And I'd like to introduce Jing Wang, who has spoken before in person at the Galactic Fidelity Work School, and I'm very happy that she's joining us again for this webinar series. She did her PhD in China and worked as a postdoc in both Germany and Australia before moving to the Kavli Institute of Astronomy and Astrophysics in Beijing. And she's particularly interested in the role of H1 in galaxy evolution. And today we'll be talking about scaling laws in galaxies. So over to you now, Jing.
Thank you, Sarah. Yeah, the audience, please feel free to disrupt me, stop me, ask me to explain things in more details if I fail to do so. I'm happy to be interrupted to discuss. Now I will start my talk about the galactic scaling laws. I would like to start with the video produced by the Illustrious simulation, which showed two rotating cubes, one for the dark matter halo and the other for the gas of different temperatures. This shows an example box where galaxies leave the typical environment they reside in. The dark matter halos, as we can see, they are not uniformly distributed in the space. They form filaments, they form knots, superclusters, and each knot, each supercluster probably several hundreds the size of the Virgo cluster, Coma cluster in our nearby universe. And our galaxies are living this type of different structures. And so does the gas. The gas, they distributed following the filaments and clusters. And they're supposed to flow along the filaments, filling into the knots, the superclusters created onto galaxies, fueling their star formation. So those environments, where the galaxies form and evolve, they quite a diversity. The different assembling history must put their prints onto the galaxies, onto the properties we observe today. Now, if we zoom in onto the galaxy populations living in the universe, direct impression is that they're quite diverse. They have different morphologies. Easy classification is put them onto Hubble sequence, dividing them into the early type galaxies that are round, velocity dispersion dominated, red, and old. And the other type, the late type galaxies, they look disky. They are supported by rotation to prevent it from collapsing due to the gravitation. And they are blue because their age are relatively young. And they have a lot of star formation, a lot of gas. There's quite a they have quite different views, and if we put them, we measure their properties, we put them into parameter space, they distribute quite widely. And in one of the most commonly used diagram today, the star forming main sequence diagram, where the star formation rate as a function of the stellar mass, then at a given stellar mass, we can see they distribute quite widely in the star formation rate values, the several orders, several magnitude of orders. They tend to concentrate into a tight sequence, which is the star forming main sequence. And but there are also galaxies deviating from the main sequence. Those are the galaxies we think they're being quenched or having already been quenched with star forming activities. These are the properties and the appearance we observe. And nowadays, it is more and more recognized that it is the flow of the baryonic material, the flow of this material in gas of different phases and in stars that drive the evolution of galaxies, driving galaxies forming these different types of appearances, pyramid properties. And if we take one galaxy, for example, it is located in the center of a hot gas halo. The galaxy accreted gas from the surrounding hot gas halo. The accreted gas would cool both thermally and kinematically, forming a rotating disk. The rotating disk can be quite extended compared to the stellar disk of the galaxy. And then with mechanisms that remove angular momentum from the gas disk, the gas can flow in and fill the different parts of the galaxy. And then in different parts of the galaxy, on very small scales, on sub-kpc scales, there's a small baryonic cycle where the H1 can cool to form the molecular gas. Molecular gas further cool, collapse, form stars. Stars evolve and feedback with metal-enriched gas. And in this way, from very large scales to very small scales, the baryonic cycle flows and drives evolution. The reason we say it drives evolution is because it is so, the different steps, they're so well linked together. If one step is get disrupted, then it will affect the other step. For example, if we cut the accretion H1, if we shrink the H1 reservoir, immediately it will affect the of the molecular gas, and then formation of stars, and the galaxy will tend to get quenched in star formation and getting old, getting red, and getting bulge dominated. As I introduced here, the galaxies, they quite diversities, they have complex physical processes ongoing within them. However, the galaxies, they show remarkably tight scaling relations between several of their properties. And these scaling relations, they give us a hope to understand the underlying physics that drives galaxy evolution. Here I plotted the baryonic cycle of the galaxy in a simpler form, in a simplified form. We start from gas equation, H1 distribution, H1 flow, and convert to molecular, forming stars and star evolve. And we, in this talk, I will focus on introducing a few scaling relations, particularly three the tightest type of scaling relations that link to three steps of the baryonic cycle. And I also will introducing a few scaling relations about the H1 mass fraction in galaxy. And these scaling relations, they result from the balance between the different physical processes and as a result of the formation history. Please, if anyone have any questions, please feel free to interrupt me loudly. Now let's start with the Tully-Fisher relation. It was firstly found by Tully and Fisher in 1977. They found there is a correlation between the optical absolute magnitude that is equivalent to the luminosity and the rotational velocity of the galaxy disk. And this relation we can immediately resemble this relation to the relation between the dark matter mass and the visual radius of the dark matter. This cubic relation, they typically defined at, for example, R200, where within which the average density of the dark matter halo is equivalent to 200 times the critical density of the universe at a given redshift. For that given density, the visual radius at 200 relates to the mass of the dark matter halo within 100 in this equation format. If we compare these two equations, it gives us an impression that if we assume the disk form with some memory about the rotation of the dark matter halo, because the galaxy form because of the gas cooling in the dark matter halo. Before the gas cool, it must be rotating with the dark matter halo. So if we assume the rotational velocity of the disk carries memory of the dark matter halo, then the similarity of these two equations here, the Tully-Fisher relation and the dark matter halo mass velocity relation, seems to indicate that the ratio of the light, optical light over the dark matter mass is close to a constant or as a function of the velocity, the rotational velocity of the dark matter halo. The optical light, which is mostly emitted by the stars, they formed in the dark matter halo in a very uniform way. Thus, in 1977, later there were more developments. In McGough 2000, there are a few improvements. The first is that we remember the first version of the Tully-Fisher relation used the optical luminosity. If we want to go from the total mass, that is the dark matter mass, to the luminosity, there is quite a few of scaling factors we need to go through in order to reach the optical luminosity. We need firstly to scale the total mass with the baryonic mass fraction of the universe, and then further scaling it with the fraction of the baryons that is within the disk that is rotating, that can be related to the rotational velocity of the disk, and then the fraction of the baryons that are in the form of stars, not in the form of gas, not in hot gas, not in cold gas, but in stars. And finally, we need to convert it as Snyder mass to the optical luminosity through the mass to light ratio of the stars. There are 4 factors between the dark matter halo mass and the optical luminosity. So in McGough et al. 2000, they firstly skip the scaling related to the mass to light ratio of the stars. They combine this mass to light ratio with the fraction of baryonic mass in the form of stars, and they use the stellar mass instead of the luminosity. So they use this stellar mass as a function of the disk rotational velocity instead of the luminosity as a function of rotational velocity, which was the earliest form of Tully-Fisher relation. And this is an important improvement because the luminosity, as we said, is indirectly related to the mass of stars. At a given mass, at a given stellar mass, the different ages of the stellar population will correspond to different values of the mass to light ratio. So a given stellar mass can correspond to a wide range of the luminosity. As the stellar population age become older, the mass to light ratio will change. So the stellar mass is a more intrinsic parameter that traces the baryonic component than the luminosity. So after changing the luminosity to the stellar mass, firstly, there is still a tight relation in the massive end, in the massive and high velocity end, where the slope in the log space is close to 4. But then at the low stellar mass end, in the region of the dwarf irregular galaxies, the galaxies data points divide from the relation established at the high mass end. And then the McGough, they did a second improvement. They further combined this factor, the fraction of baryons residing in the disk with the first two factors. So they replace the stellar mass with the baryonic mass, put the baryonic mass on the y-axis. Then between the baryonic mass and the total dark matter halo mass, there's only one remaining variable factor, that is the baryonic fraction of the universe. By doing so, we can see clearly from the figure, the baryonic mass and rotational velocity, and they form a very tight relation throughout the whole velocity range and the whole mass range. It suggests this relation is much more, probably much more intrinsic than the relation on the left side. So this is the famous baryonic Tully-Fisher relation established in McGough et al. 2000. The slope or the power law index is close to 4. And let's compare the newly established baryonic mass Tully-Fisher relation to the relation between the dark matter halo mass and the visual velocity of the dark matter halo. Let's put them together again as we did for the first Tully-Fisher relation. We still see the format is very close, and the similar format of the two equations they suggest that when the disk form within the dark matter halo, there must be a perfect balance between different mechanisms that keeps the proportionality so well, so that the mass, the same fraction of the mass that gone into the disk, the baryonic disk, will be accompanied by similar fraction of velocity that going into the velocity of the disk. So to form the baryonic Tully-Fisher relation. This balance is so accurate, so delicate, it caused a problem for the lambda CDM. Basically, with the lambda CDM simulation, when they try different kind of semi-analytical model put on the dark matter assembling history, they found it really hard to form the observed tightness of the Tully-Fisher relation, the baryonic Tully-Fisher relation. Here in the left figure from Sales et al. 2017, the gray data points from observation, the baryonic Tully-Fisher relation, and the red shaded region is the prediction from simulations. So we can see from the simulation at the low mass end and low velocity end, the Tully-Fisher relation becomes steeper than observation. And this is because in simulation, there has to be a feedback, stellar feedback at the low mass end in order to suppress the formation stars in low mass halos in order to match the stellar mass function observed in the local universe. In order to do that, they have to add feedback that produced the correct stellar mass function, but however, it caused the deviation of the Tully-Fisher relation from observation. So this caused a problem and still needs solving in the future. That was what we want to say about the Tully-Fisher relation. Now let's go to the second step within the halo, how the H1 is created, form a disk, and then form the stellar disk. I would like to start with the semi-analytic model from Wormau and White, 1998. That model, they almost formed the basis of the semi-analytic model that produce disks in lambda CDM simulations nowadays. It is still commonly used after 20 years' time. That model says that the RD, which is the scale length of the baryonic disk, they are scaled with the visual radius of the dark matter halo at 200, which is the radius of the dark matter halo within which the average density is 200 times the critical density of the universe at a given redshift. It is scaled, the disk radius is scaled with the visual radius of the dark matter halo. And the parameters that link these two radius, including most importantly, the spin parameter of the dark matter halo, which is the dimensionless measure of the angular momentum of the dark matter halo. Basically, it describes how fast the dark matter halo is rotating. It says that if it rotates faster, then it will form a disk with a relatively large scale length. If it rotates slower, it is the other way around. And also this parameter that basically describes how much fraction of the angular momentum is conserved during the formation of the disk, and how much fraction with respect to the dark matter halo mass can be formed into the baryonic disk, can be formed the baryonic disk. And with this relation, we expect that the disk size, the disk size is predetermined largely by the property of the dark matter halo where the disk galaxy form. And it was found earlier days that indeed from the optical observations, the size mass relation for the late type galaxies and the early type galaxies, they're formed in a way that the correlations are formed in a way that very closely resemble those that would be predicted by lambda CDM simulations with the small, Mao, and wide model. They form this relation for the disk type galaxies with a slope that is close to 0.3, and this relation for the early type galaxies that is with a slope that is close to 0.4, 0.5. The early type galaxies and late type galaxies, they follow different size mass relations, because for the late type galaxies, it is mostly a disk, but for the early type galaxies, there is a bulge in addition to the disk. And when the bulge form, according to the early simple format of the semi-analytic model, part of the rotation of the original stellar material that would form the bulge at the present will go into the disk at the present, like the equation here. Okay, so this early days optical size mass relation give confidence to this relation. But when it comes to the H1, the story seems to be different. Firstly, there is still a size mass relation for H1 disk, where the diameter is the size is defined as a semi-major axis of the azimuth at a subdensity of 1 solar mass per pieces squared. And secondly, the relation is highly tight, is very tight. The scatter is only 0.06 dex in the vertical direction, or 14% uncertainty. And thirdly, the slope of this relation is very different from that of the optical relation. The slope is close to 0.5. Basically, it says that the H1 mass is close to the power of 2 of the H1 disk size. It basically indicates that the different H1 disks, they have a similar characteristic averaged surface density. They have very similar surface densities within the characteristic radius. This is very different, the slope very different from that of the optical disks. And the relation is also much tighter than the optical size mass relation. It is so tight, and it basically indicates that it would not allow much space for other variables to play a role in determining the relation. As we said in the Mao-White model, the spin, the fraction of mass that would go into the disk, the fraction of the angular momentum that would be conserved, will all determine how the size of the disk form. But here, this relation is highly tight. And most remarkably, additionally, we notice that the relation here, it includes the Milky Way type massive galaxies, M31 Andromeda type massive galaxies, but it also contains the small Magellanic Cloud type dwarf irregular galaxies and dwarf irregular galaxies of even more smaller masses. From the typical semi-analytical model, we would not expect these galaxies of different masses to lie on the same size mass relation, simply because the star-forming efficiency, the efficiency of converting the baryons, the hot baryons into the cold baryons, and further from the cold baryons into stars, the efficiencies are very different in different mass regions. For the Milky Way type galaxies, spiral galaxies, the efficiency is usually relatively high. But for the dwarf irregular galaxies, those efficiencies are usually very low. And also the star-forming history in these two types of galaxies are different. In spiral galaxies like the Milky Way, the star-forming history tend to be relatively smooth, continuous. But those in the dwarf irregular galaxies, they tend to be bursty, stochastic, because as we know from the baryonic cycle of the gas and stars, the gas and stars are linked on the same cycle. The different star-forming history, different current level star-forming efficiency, they show the feedback onto the gas in the galaxy. We would expect the low mass galaxies to have higher scatter on this relation, to have a different slope in this relation when compared to those of the more massive galaxies. But in fact, we didn't observe such an effect. We just see them lie perfectly on the same relation. And if we want to further investigate why this relation form, we look into the radial distribution of the H1 surface density, the H1 surface density as a function of galactic centric radius. We found that except for the early type galaxies, which are marked by the reddish color, pink color here, the late type and dwarf irregular galaxies, they have very similar homogeneous looking H1 radial profiles in the outer regions. When the radius are normalized by the characteristic radius, which is the definition of the size-mass relation, they look highly self-similar. That's why the different galaxies, they lie on the same size-mass relation. As we said, this is not expected from our knowledge of how galaxies should form in semi-analytical models, in common semi-analytical models. And indeed, it caused a problem for them. This was presented in Bach et al. 2016 when they tested the Eagle simulation dataset, the simulation, how they produce the size-mass relation with H1. They found that there is quite a fraction, around 40% of the simulated galaxies that have huge holes in the H1 disks. And those galaxies, they would divide significantly from the observed size-mass relation. The observed size-mass relation is the green line here with the dashed line as the 1 sigma scatter. And the blue are those good simulated disks without unrealistic holes. And the orange shaded regions are all the galaxies produced by the simulation, including those with unrealistic holes. And then we can see the orange thing, the distribution, they tend to divide from the observed relation and with much larger scatter, with a steeper slope and a larger scatter. The red panel is displaying similar thing, but with a different formula of the model that converted the drive the baryonic cycle, converting gas to stars. They basically show similar result and actually worse result. It is very hard for simulation to produce a correct observed size-mass relation. You basically need the H1 in the simulation is very sensitive to the feedback formula, the stellar feedback, supernova feedback, and adjusting that slightly would cause a big change in the H1 radial profile. So it seems a detailed balance is really required in order to produce the observed size-mass relation. And still we notice that here the H1 mass only extend to 8.5 dex. In observation, you see we already extend all the way down to 7. They are concentrated in this part, but they already have a problem. And similar problem actually also in nowadays the TNG, illustrates TNG, usually due to the resolution limit, they do not extend to the really low mass end of the observed size-mass relation. Now let's go to the second step, the third step. When we have the H1 distributed into a disk and flow into the inner star-forming disk, how the gas is used to form stars. This can date it back to a Kennicutt-Schmidt relation. Firstly, early form of Kennicutt-Schmidt relation in 1998. Actually, it could be dated back even earlier, but this figure, which often commonly display in talks presentations, is dated back to Kennicutt 1998. Here it showed that there is a relation, tight relation with a slope of 1.4, which is the star formation rate surface density as a function of the total gas surface density. Here, when saying gas, it's a sum of the atomic hydrogen H1 and the molecular hydrogen. The slope 1.4 is make people very excited because it's very close to 1.5, and 1.5 is a type of star formation law one would expect from the gas disk with very simple assumptions. Basically, we can go through such a theory with the equations on the left. If we assume the scale height of the gas disk scales with the surface density of the gas with a power law index of beta, then the volume density of the gas would scale with the surface density of the gas with a power law of 1 minus beta. And then the free fall time of a gas cloud is calculated as thus related to the volume density of the gas like this. So it would be proportional to the surface density of the gas with a power law like this, which is beta minus 1 then divided by 2. And now we can use the gas surface density divided by the free fall time to resemble the star formation rate. So the star formation rate would be proportional to the gas surface density with a power law of 1.5 minus beta over 2. And if beta is 0, which indicates a constant disk scale height, a scale height that is irrelevant with the surface density of the gas, then the power law index would be exactly 1.5, very close to the slope of 1.4 discovered earlier days by Kennicutt and Schmidt in the relation star formation rate surface density as a function of the gas surface density. But in that relation, we can already notice a few things. The first is that it is not perfectly extended to the low surface density end. We can see at the low surface density, the relation tend to become steeper. And also at that time, the other problems, one is that they do not have a lot of resolved H1 maps observed at that time. So what they did is they took the total H1 mass and divided by the optical disk size to get the H1 surface density, and then add the molecular surface density. Using the optical disk size to resemble the gas disk size is okay for the molecular gas, because most of molecular gas concentrated on the optical disk. But nowadays we know it will be a severe problem for the H1 gas, because for the star forming galaxies, the H1 disks, they typically extend to 1.5 times to 4 times, even 6 times the optical disk size. But we will come back to that later. Later, when nowadays with better observations, better resolved maps, how would that relation evolve? But before that, we need to mention that people later found there's even a tighter relation between the star formation rate and the density of the dense gas, HCN. The slope is very close to 1 exact, and not 1.5 or not 1 point, and not 1.5, not 1.4. The slope is close to 1, and this is worth mentioning here because the slope of 1 is almost equivalent to saying that the dense cloud is so closely related to the final stage of star formation that it is like a cloud counting, that each massive cloud would form a fraction of stars with almost a linear relation, not a power law relation. But the HCN, though this dense gas, it is more closely related to the star formation. It is very hard to observe beyond the Milky Way. And even nowadays, when there is a imbed survey that finally extend the sample of galaxies with resolved HCN maps to a few tens nearby galaxies, that is only achieved these recent years. There are very few observations. It's very hard to observe it. In most cases, we only observe the H1 gas and the molecular gas. We need to relate those two phases to the star formation rate in order to get a understanding of the star formation law. And it is not just a compromise. It is also because of the nature of the baryonic cycle. As we said, the different steps, they closely linked. So in order to understand how stars form out of the gas, we do not only need the final step of converting the dense gas into stars, we also need to understand how the star formation is linked to earlier phases, like the diffuse molecular gas, CO, and hydrogen molecular, and also between the star formation rate and atomic hydrogen gas, H1. Now we come back to those two phases, and with later development compared to Kennicutt 1998. And this was established with the SIN survey, the SIN survey, hierarchical survey, Bimason survey in 2008 by the group Leroy et al., Biguel et al. And these are figures from Biguel et al. They obtained the highly resolved maps for the H1 gas and molecular gas for more than 30 around 30 nearby galaxies. They resolve the gas to the scale of sub-KPC scales. And their finding, the second improvement, in addition to higher resolution, is that they separately look into the relation of star formation rate subdensity with the H1 subdensity and the molecular subdensity. And the result as shown here is very clear. Within the R25, within the optical radius, in sub-KPC scales, the star formation rate, they are very weakly correlated with the H1 subdensity, but tightly correlated with the molecular hydrogen subdensity with a slope close to 1. So it is perfectly consistent with the baryonic cycle, where the molecular gas is a closer step to star formation than the atomic gas. But the atomic gas are not totally dissociated from the star forming step. When we have a larger dynamic range, when we combine when we take the low surface density regions beyond the optical radius, when we extend the dynamic range of less than 1 dex to nearly 1.5 dex, here we can see there's still a weak correlation between the star formation rate subdensity and the H1 subdensity. So it suggests that the H1, although it's linked to star formation rate, is weak. It is not totally irrelevant. It is still linked to it. It's just weaker than the relation between star formation rate and the molecular gas. The role of H1 in fueling the star formation rate is still remembered by the final star formation rate we observe in a galaxy. Now there are more modern developments of the Kennicutt-Schmidt law, and there is a extended Kennicutt-Schmidt law where they change the x-axis into the gas subdensity multiplied with the stellar surface density with a power law index of 0.5. They found if so, they can put the galaxies, both dwarf galaxies and spiral galaxies, onto the same very tight relation. They solve the problem of the old Kennicutt-Schmidt law, where when one put the total gas molecular plus atomic on the x-axis, the slope changes at the low gas surface density end. Basically, they are saying that the stellar surface density, it plays a role in the conversion efficiency, converting the total gas to the star formation rate. If we take that efficiency into consideration, we get a tight universal relation for the low mass galaxies and high mass galaxies. If we did not take into account this contribution from the stellar surface density, and the dwarf irregular galaxies, it would divide from the relation with a steeper slope, and that is lower efficiency of forming the stars compared to the spiral galaxies. And another development is the volumetric Kennicutt-Schmidt law, and they used the information of the velocity dispersion in the gas disk. They used the quasi-equilibrium model that the disks are in quasi-equilibrium between the gravity and the pressure, so that with the velocity dispersion and the gravity, one can derive the scale height of the disk. And with the scale height derived, one also got the volumetric density of the gas. And with some assumption about the ratio between the star formation rate scale height and gas scale height, then one can also derive the star formation rate volume density. So this volumetric Kennicutt-Schmidt law, they changed the surface densities on both axes to volumetric densities. And they found that after doing so, there's both a very tight relation for the molecular gas and for the H1 gas. And they found that when the tightest correlation are found, the H1 disks in a flaring form. The molecular gas disk is in for the not flaring with a constant scale height. And another remarkable thing is that when one consider the volumetric star formation, or as they do, they found the scatter of the relation in the H1 is actually smaller than that of the molecular gas. It is very contrary to the previous finding and very contrary to our normal understanding of the baryonic cycle. It basically says the H1 is more closely related to star formation than the molecular hydrogen. This is very interesting and causing a debate of the way that the stars form. This is something that will be under development in the coming years, I believe. Now we have introduced three well-known relations: the Tully-Fisher relation between the dark matter mass, between the rotational velocity of the disk and the baryonic mass of the disk, and the size mass relation of the stars and of the H1 gas, and the Kennicutt-Schmidt law of how to converting the gas, both atomic gas and the molecular gas, to stars. And now we go to the scaling laws of H1 mass fractions in a galaxy, which should be the result, the consequence of so the many different processes they combined together. They combine together makes the scaling relation of the H1 mass fraction in a galaxy. This a result from the X gas survey. X gas survey is very different from a traditional blind surveys. like alpha or high pass. They are targeted survey for selected galaxies. The galaxies are selected to have a representative sampling of the parameter space as a function of stellar mass. So basically, it can be viewed as relatively representing a full population at a given stellar mass. By doing so, compared to the traditional blind surveys, blind and shallow surveys, they can detect much gas poor regions, and they can derive the representative median relations of H1 gas fraction as a function of other properties, because the detection rate is quite high. The survey go quite deep. There are few upper limits for non-detections, but they would not affect statistics like the median values at a given stellar mass, at a given other properties. So by doing so, they could be able to measure how the H1 mass fraction, which is the H1 mass over the stellar mass, change as a function of other properties. Now here, change as a function of the stellar mass, averaged surface density, and the NUV minus R color. We can see the correlation, anti-correlation and anti-correlation. It basically says that the gas fraction drops when the galaxies are more massive, of higher surface densities, more early type, more bulge dominated, and redder. Redder means they are older. So it is consistent with our understanding of galaxy formation, that the more massive galaxies, more bulge dominated galaxies, older galaxies, they just older and more evolved, and these figures clearly show that they are more evolved, either because they have fewer gas or they are accompanied by fewer gas. And another important thing from the figure is that they do not only provide the trend, they also provide the slope that set exactly by representative population in the universe. So any simulation that would like to reproduce a real universe, they need to produce these relations not only with the same trends, but also with similar slopes, the same slopes. And we can go deeper. We can investigate more scaling relations about the H1 mass fraction that could give insight to other to different processes ongoing in galaxy. And there was known to be a relation between the gas phase metallicity and the stellar mass. Sorry, here the year should be 2004, not 2014. Anyway, here we can see the correlation. The more massive stars, they have higher gas phase metallicities. And the interpretation at that time when the paper was written was saying that the high mass galaxies, because of the higher gravitational, higher gravity, they are more able to maintain the gas, particularly those precessed gas from the evolved stars, so that they can keep the metals. But for low mass galaxies, because their potential well, gravitational potential well is shallow, and when there is a stellar feedback, the chemical enriched gas, metal enriched gas would escape from the galaxy. So the metallicity remains low. That was the interpretation at that time. And later in 2012, in Yats et al. And others, they investigated the scatter of the metallicity stellar mass relation. They want to understand what drives the scatter. They found that one of the key parameters is the star formation rate. And they found it behaved differently in low mass galaxies and high mass galaxies. In low mass galaxies, it seems that at a given stellar mass, the lowest deformation rate is related to higher metallicity. But at the high mass end, it is the other way around. It is lowest deformation rate related with lower metallicity. And their interpretation at that time is that the reason the gas phase metallicity is related with deformation rate is because the gas phase metallicity is related with the gas accretion, the raw material, raw material H1 accretion that would dilute the metallicity in the galaxy. And then in 2016, in Brown et al., they directly were finally able to investigate the driver of the scatter of the metallicity mass relation with really observed H1 data. They use the alpha data. They stack the spectra. They stack spectra in subsamples that defined by different parameter bins. So by stacking, they get a higher signal to noise ratio. They contain thousands of non-detections into detection, get a measure of the average the H1 mass fraction in that parameter bin. And by doing so, they want to investigate which is more intrinsic in driving the scatter of the metallicity mass relation. Should the driver be the star formation rate directly, or should it be gas accretion, as Yates et al. Speculated? And here the figures, they plot the gas phase metallicity as a function of stellar mass, color coding the different bins at a given stellar mass by the level of H1 mass and by the level of star formation rate. But from the color coding, it's less clear to see the trend, although we already can see, I believe you can already see trend there. It goes down, goes up, goes up, goes up. But it's clearer to see them in direct data points. In the average data points in bins of stellar mass, and then the properties as a function of the metallicity. So the top row and the bottom row here, they are basically equivalent. They are just different ways to plotting the same thing. And it's clearer from the bottom panel, and we see that for a given stellar mass bin, the H1 mass is anti-correlated with gas phase metallicity. And for the star formation rate,
sorry,
yes.
Coming up to the hour now, so just letting you know.
Oh, I didn't know. I thought I was, sorry. I will finish very quickly. And for the star formation rate, the trend is not monotonic. The slope will change from the negative to positive. So basically, the comparison of the two panels suggests that the H1 gas might be the more intrinsic parameter that determines the scatter in the gas phase metallicity stellar mass relation. More gas would mean that there are more accretion of the metal pore gas, and that's why the metallicity is diluted and become very low. I think since the time is very close, I will just skip to talk a bit about the environment and then stop the talk. As we most of the processes we said earlier about the secular evolution taking the galaxies as a system of its own, but as we said, all galaxies, they live in an environment. So the studies investigates how the H1 mass fraction determined by environmental parameters like the dark matter halo mass and the local density of galaxies. Here the sigma 7 is a measure of average the number density of galaxies within the distance of the 7th labor is a measure of local density, and halo mass is a measure of dark matter halo. So in Brown et al. 2016, they firstly investigated the H1 mass fraction as a function of stellar mass in different halo mass bins. They found that at a given stellar mass, galaxies with lower halo masses, they tend to have higher H1 gas fractions. And so it's a clear evidence of satellite galaxies H1 gas fraction depends on the halo mass, depends on the halo assembling history, and it depends on the environmental processing. And they further want to figure out whether the local density or small scale environmental effects like the tidal interactions would play a more significant role than the halo mass, as it is closely related to the halo mass. We expect high local densities in higher halo masses. So they plot the red figure. We can firstly compare the cyan with the blue line, and we see that for the same halo mass bin, the different local density property and the gas fraction difference at a given stellar mass is on the order of 0.1 dex. And if then we compare the cyan curve with the pink curve, where one basically control for the local density and comparing bins of different halo masses, we can see the difference in that to around 0.2 dex. So the difference in halo mass is causing a larger difference in H1 gas fraction than the difference in local density of the galaxies. So it suggests that for the majority of satellite galaxies, the halo mass play a more important role than the local density in determining the gas fraction in the galaxy. I will skip the remaining figures, but we're very close to the summary anyway. Sorry for taking longer than I expected, but I'm happy to take questions.
Thank you. Thank you, Jing, for an excellent overview. Do we have any questions from the audience? I have a message here from Josh, who says, "Hi, Jing, many thanks for your presentation."
Thank you, Josh. I'm happy you come.
And yes, if you'll provide a copy of your slides, then people can also catch up with the ones that you needed to skip over. Would that be okay?
Certainly.
Yeah. Any questions to the audience? In the meantime, I was wondering about those unphysical galaxies that you said have holes in the simulations. Is it not possible to get some where the gas is accreted very recently, and so it hasn't flown to like the center or migrated?
Certainly, because there are quite a lot of outlying gas, quite a considerable fraction of those outlying gas in the extended disk must be newly accreted. But meanwhile, in that set of simulation from EGOS, they found the stellar feedback, supernova feedback is making the situation worse. It produce a gas surface density profile that is too shallow. And when one views the image from two-dimensional map, it has unrealistic holes throughout the disk from small radius to large radius.
Yeah. Cool. Thank you. And if there are no other questions from the audience, then please unmute and let's give Jing another round of applause.
Thank you. Okay, thank you for inviting me.
Thank you for
hope
coming.
to see you again next sometime.
Definitely. I'm just going to stop recording now, but I'll stay on the line.